Hi, today we're going to be looking at another example about AC power. So, the problem is like this. We have a circuit that has an input voltage, a total current, and an unknown impedance. What we know about the circuit is the current, the total current, which is equal to 4.24 times sine of 5 kT plus 45 degrees. We know the active power, which is 180 watts. And we know that the power factor is 0.8 lagging. And with this information, we need to find what our total impedance is. So, we can start with the power factor. With the power factor, we can calculate two things. We know that the power factor is equal to P over the magnitude of S. So we have the power factor and we have P, so we can calculate the magnitude of S. And we also know that the power factor is the cosine of the angle of phi, which is the angle of our power, of our complex power. So we can also calculate the angle here. So first, we are going to calculate the magnitude of S, which is P over the power factor. And that is basically 180 over 0.8. And that gives me 225 VA. And now, we also know that the cosine of phi, which is my power factor, is equal to 0.8 lagging. Yeah, so we can calculate 5 by taking the inverse of cosine. Where's that? And that will give me phi. So that gives me 37 degrees. So 37 degrees. Now, as I mentioned in one of our previous videos, the cosine of phi will give me the same number as the cosine of minus phi. So by knowing that we have 0.8 as cosine of phi, we don't know what the angle of phi is what the sine of phi is. It could be positive or it could be negative. But we do know that it says here lagging. And we said that circuits that are where power is lagging are mainly inductive, and therefore the sign has to be positive. So this positive sign comes from the fact that we know that our power factor is lagging. If it was leading, the sign would be negative. So like this, we already have my complex power, which is its magnitude, 225, and its phase of plus 37 degrees. So that's the power. Now, with this power, and this current, we can calculate our input voltage. The current, I'm going to need the omega when we calculate the final reactive component. But right now, I'm just going to represent my total current as a phasor. So my total current would be 4.26, I believe, to 4, with an angle of plus 45 degrees. We need to have the complex, the so we need I total complex conjugate RMS, and that would be 4.24, sorry, this is amperes, over square root of 2, with an angle of minus 45 degrees, because we have complex conjugate here. So this complex conjugate makes that my sign becomes minus. So my total conjugate is equal to 3 at minus 45 degrees amperes. So we can calculate our VRMS, because we know that S, so from here, no, haven't written it yet. So we know that our complex S can be in general calculated by BRMS, the RMS of the input voltage, times the RMS of the complex current complex conjugate. So I have this term, which is this one here, and I already calculated my S up here, which is there, so I can calculate my input voltage RMS. So VI RMS is then equal to S over I complex conjugate total RMS, which is then the S that we had here, 220 at 37 degrees, 225 was it? 225 at 37 degrees VA over 3 at minus 45 degrees VA, sorry, amperes. So my input voltage RMS becomes 75, which is 225 over 3, with an angle of 37 degrees minus 45 degrees, which is plus 82 degrees. And this is volts. Now, with this voltage, I can calculate then my total impedance, which is the the input voltage over the total current. Over the total current. In this case, not complex conjugate. So that would be 75 with an angle of 82 degrees volts over my total current RMS 3 at plus 45 degrees, because I don't want it complex conjugate anymore. So my total impedance is going to be 75 over 3, which is 15. No, not 15. 25, yeah. 25 with an angle of 82 degrees minus 45 degrees, which is 37 degrees. 37 degrees. Now note that my total impedance, the angle of my total impedance, has the same angle as my total power here. So, in Cartesian form, my complex impedance looks like this: 20 plus 15 j ohms. So, we can plot it. Here. In the complex conjugate plane, sorry, I wanted to be on the line. In the complex plane, this is real. and this is imaginary. So I have 20 on the real axis, so I will have 5, 10, 15, 20 on the real axis here, and 15 on the imaginary axis, 5, 10, 15, so 15 here. So my impedance vector looks like this. Yeah. And I have an angle of phi, which is the same angle as the angle of our power. And we have 15J there. We have a positive reactance because we have plus there, which means so we have basically our circuit looks like this. We have a real impedance, and the real impedance is our normal resistance. So my circuit has a resistance in series with an element that has got a positive reactance, which is an inductor here. So my resistance has got 20 ohms. My reactance has got a value of plus 15J ohms. And now comes the omega here in play, because we need to calculate the value of L here. And we know that the impedance of an inductor is J omega L. So we know the impedance of J omega L of the inductor, and we know the frequency at which it's got that impedance. So we can calculate L equals ZL over J omega, which is equal to 15J over 5K J, which is 3 millihenries. So this is 3 millihenries. So yeah, that's how we calculate. So basically, as you can see, we're not doing anything but just manipulating complex numbers with the concepts that we learned about AC power and S. One thing I would also like to plot here, just for the sake of argument, is the complex power here. So we have the complex power is 220. So I'm just gonna. So what we could do is, I'm gonna plot more or less that, like that I plotted here. Real and imaginary. So 4 to 3. So 1, 2, 3, 4 here. So this would be my complex power. I have the same angle as my impedance there. My magnitude here is 225. My power, my active power is here, which is 180 watts. And my reactive power, we can calculate here. So P would be the magnitude of S times, Q, I want Q, times sine of phi J, and that's gonna be (225) times sine of 0.8, sine of 37 degrees, which is 135. So here I have 135 and 36 and 35 bars. Yeah. So that's how it looks like. The impedance has the same angle as the power, and I have my active power, my reactive power, my total power, and the circuit that generates these conditions is this one. A resistance of 220 ohms in series with an inductor of 3 millihenries, provided that our power source gives me a frequency of 5 kiloradians per second. So that's it for this video, and thanks for watching.